Today we will be discussing an interesting article entitled Organic Chemistry in Water. First published in 2005, this article aims to discuss some of the ways in which water is emerging as a more versatile solvent in organic chemistry reactions. Water has many advantages as a solvent, including being the most inexpensive and environmentally benign option. Additionally, where water was once believed to slow down or even halt certain reactions, this paper details the ways in which the opposite is actually true. For some organic chemistry reactions, water has been found to accelerate the reaction and enhance reaction selectivities. Water has also been found to be able to facilitate air-sensitive transition metal catalysts in open air, improving the efficiency of certain reactions. Another way in which a water solvent has been found to increase synthesis efficiency is that some reactions have been found not to need protection of certain functional groups when performed in the presence of a water solvent. Our discussion today will focus on pericyclic reactions such as Diels-Alder mechanism, 2-sigma, 2-sigma, 2-pi cycloaddition, and the Claisen rearrangement. We will also look at reactions of carbanion and carbocation equivalents.
Pericyclic reactions are important in organic synthesis due to its ability to control stereochemistry while constructing cyclic structures. It involves a transfer of electrons within the pi system and create new sigma bonds. In this paper, two types of pericyclic reactions were studied. These reactions will both end up with two new sigma bonds as seen later. First, we will go over Diels-Alder mechanisms. Since the discovery that Diels-Alder's reaction, a pericyclic reaction, proceeds up to 700 times faster and have a higher endo-exo selectivity in water compared to organic solvents, there have been extensive experimental studies on this topic. The mechanism of Diels-Alder shows the transfer of electrons from the double bonds to create new bonds and a new cyclic structure. In this study, the reactants are trans-trans 2,4-hexadienyl acetate and N-propyl-myelamide, as seen here. The two structures were reacted in different solvents listed. This table shows the rate of acceleration of Diels-Alder's reactions by different solvents. As seen in the table, water was the fastest solvent. The reaction is faster in product solvent like methanol than non-product solvents like toluene. This suggests that hydrogen bonding and hydrophobic effects may be important for the acceleration. This is another reaction that involves the transfer of pi bonds to create new sigma bonds, just like Diels-Alder's. The starting material is a little different from what we just saw due to the extra carbon that is non-planar. Similar to the Diels-Alder's reaction, the rate of acceleration of the reactants also showed the significant difference when the solvent is protic versus aprotic. But most importantly, water by far had the fastest reaction time as seen. Water only needed 10 minutes for the reaction to complete, as opposed to toluene and ethyl acetate needing over 120 hours. The Claisen rearrangement is a carbon-carbon bond-forming chemical reaction. The heating of an allyl vinyl ether will initiate a 3,3 sigma tropic rearrangement to give a gamma sigma unsaturated carbonyl. Unlike other pericyclic compounds that was discussed in this paper, where the reaction time was the primary topic, the Claisen rearrangement was studied for the yield of the product with different solvents. Though it is known that heating the reactants can create the gamma sigma unsaturated carbonyl, this experiment was done at room temperature. From this, they discovered that aqueous solvents was much faster compared to the organic solvents and had a perfect yield by the end of the 5th day. The mechanism is the same as any pericyclic reaction where the transition of the pi electrons form a sigma bond. However, there is an additional step at the end of tautomerization to create an alcohol group.
Before discussing the next topic of the article, reactions of carbanion equivalents, I want to briefly review Barbier and Grignard reactions. The Grignard reaction is a very important reaction involving organometallics in which new carbon-carbon bonds are formed. Because the Grignard reagent, an organomagnesium halide, is extremely nucleophilic, it would be protonated if the reaction were performed in the presence of water. Therefore, the reaction must occur in a dry environment. Protonation of the organomagnesium halide would destroy it, and thus the reaction could not proceed to form the new carbon-carbon bond. With all that being said, the Grignard reagent must be formed separately from the reaction container. The Barbier reaction, while very similar to the Grignard, can be performed in situ. However, while performing background research regarding the difference between the Barbier and Grignard reactions, I found at least one article from 1982 challenging this assertion that the Barbier reaction occurs in situ. The mechanism shown here is for the Barbier reaction, where we see the concerted pathway that results in a tertiary organomagnesium halide, which will be worked up with water to form a tertiary alcohol. Some of the carbanion equivalent reactions discussed in this article were rhodium-catalyzed addition of aryl groups to aldehydes, as well as phenylation and alkylation in water. If we look at the reaction equation labeled scheme 7, we see that a rhodium-catalyzed addition of an aryl group to an aldehyde can be done in an aqueous solution. Next, we can see an example of a phenylation in water. Phenylation reactions are ones that result in the addition of a phenyl group to a molecule. One way of adding a phenyl group is through the use of the aforementioned Grignard reaction, which requires the use of the highly reactive organomagnesium. The reaction shown below, phenylation in water, does not use an organomagnesium molecule, but rather an organotin molecule. An organotin molecule is one that contains at least one carbon-tin covalent bond. This reaction is possible because the methyl group that would usually be present in the organotin molecule has been replaced with a halide, specifically chlorine for this example. Replacement of the methyl group with a halide requires the use of a base, which will increase reactivity. The catalyst used in this reaction is a rhodium catalyst. Rhodium is often used as a catalyst because of its stability. The mechanism for this reaction is believed to be similar to that of alkylations in water. The reaction shown below is one such example of phenylation occurring in an aqueous solution. Additionally, the aldehyde does not require the use of a protecting group in this reaction, despite the presence of its hydroxyl group. The next reaction we will discuss is alkylation occurring in water. The mechanism below is a proposed mechanism for the addition of an alkyl halide to an aldehyde in water. In this mechanism, copper acts as the transition metal catalyst to activate zinc and initiate radical formation. The zinc-copper couple will react with the alkyl iodide, labeled as R'(I) in the drawing, and a radical anion will be formed. This radical anion may then react with the aldehyde, in which one electron from the double bond between the carbonyl carbon and the oxygen will couple with the radical previously formed. The other electron of the double bond may couple with an electron from the indium to form an indium alkoxylate. Treatment with water will result in a hydrolysis of the alkoxylate, which may result in the formation of an alcohol such as the one shown below.
Another study done was to see the use of water for reactions including carbocations. In organic reactions, carbocations are often initiated by Lewis acids. There are many acid-catalyzed reactions of carbocations that are used in the chemical industry. However, it is important to note that these reactions generally are moisture sensitive, since water will react with the acid instead of the substrate via acid-base reactions. This will not only halt the intended reaction, but will create a completely different product. To avoid this from happening, there have been new findings of Lewis acids that have been found to retain catalytic activities in aqueous solutions, and better yet, those that can be activated by water, such as earth metals. Mukayama-Aldol reaction was studied under aqueous solution and dry organic solvents to see the effectiveness of each. The mechanism of the Mukayama-Aldol reaction is the following. First, a nucleophilic attack from the lone pair of the oxygen to the earth metal, and the leaving group leaves. In this case, the earth metal is the ytterbium trifluoromethane sulfonate, which is found to be highly effective for catalyzing Mukayama-Aldol reaction of benzaldehyde with silyl ether in aqueous solution, and much less in organic solvents. The leaving group attacks silicon so that it can leave as a leaving group, giving the oxygen a negative charge. This negatively charged oxygen reforms the carbonyl double bond. Now this carbon has one too many bonds attached, making the former double bond attack the carbonyl carbon, undoing the carbonyl double bond. There is another nucleophilic attack from the water to the earth metal, kicking out the leaving group. And finally, a proton transfer to create an alcohol group. It's important to mention that the final product will be a racemic mixture, since it started with an aldehyde, an sp2 hybridized molecule. So when the nucleophilic attack occurs, it can be attacked by either the front or the back. From this experiment, it was concluded that aqueous solutions were 9 times more effective than that of dry organic solvents. The The enhancement of the reaction rate by water is thought to be due to the change of acid catalyst structure caused by the water, or the regeneration of the active catalyst from the corresponding intermediate, which is faster in water than organic solvents.
The articles summarized here discussed more reactions in water than those that were highlighted in this presentation. As previously mentioned, this paper was first accepted and published in 2005, so there have been many new discoveries since the publication of this paper. Due to the low environmental impact of water as a solvent, research must continue to be done on these reactions for their contributions to green chemistry. In addition to the environmental impact, as discussed, many of these reactions actually proceed more efficiently and with better yields when performed in aqueous rather than organic solvents. To briefly recap, this presentation focused on pericyclic reactions and carbanion and carbocation equivalent reactions in water.